Okay, in this lesson we're going to take what we learned about the solar energy coming in, and we're going to see how it moves around the Earth. That is a key question for weather because all of the weather is controlled by that motion, that idea that energy is coming in from the sun at different levels in different parts of the Earth are receiving more, and the Earth wants that to balance out. It wants everybody to have the same amount of energy. If the Earth had its way, we all would have the same temperature at the North Pole, South Pole, at the equator, wherever. It doesn't, and that's what weather is all about, that contrast in temperature. So, in order to do that contrast and figure out what's going on, we've got to understand heat transfer within the Earth, between the Earth and the atmosphere. It's a whole system of transfer there, so we're going to look at that in some detail here in this section. So first, let's define temperature. Temperature is proportional to the kinetic energy of atoms or molecules. So what are we talking about? Well, an atom moves, and so do molecules. They have a motion to them. That motion, the faster it is, the hotter the temperature. The slower it is, the cooler the temperature. That motion is what's proportional to temperature. So you think about a gas, molecules are relatively far apart. They're going to tend to move a little faster maybe. But you think about water, molecules a little bit closer together, they might not move as fast. So temperature from those molecules in the atmosphere is a direct reading of how fast those molecules are moving. Now, let's change how those molecules move. How do we do that? We got to bring heat, which is energy transfer, into them. So somehow heat has got to get into these molecules to change their motion. So there are various ways of heat is moved. We're going to talk that you're going to see all kinds of things about temperature scales, how we measure temperature in the book. And rather than go through that here, let's just go to temperature processes. Second law of thermodynamics says heat flows in response to a temperature gradient. Did you ever accidentally touch something really hot? And you're quite cold, probably, compared to that hot. The heat that was transferred was being transferred to your skin from that hot object. That's basically all the second law of thermodynamics is saying. Heat flows in response to a temperature gradient. It will always flow towards lower temperature, in this case, your skin. So there was a transfer of heat. Now, there are four various ways heat can transfer. Radiation, which we talked about in a lot of detail with the sun. That's how the energy comes from the sun. That's how heat transfers from the sun. Conduction, which I just demonstrated with your skin touching a hot object. Convection. We've heard about convection ovens and all that. Or if you ever look outside and watch a big bubble of a thunderstorm developing and stuff, that's convection. Heat being moved around. Watch water boil. You'll see these bubbles start at the bottom of the boiling pot of water and move towards the top. That's convection. Again, conduction. Each one of these is playing a role. Latent heat is all related to phase change between a liquid, solid, gas phase change. So we're going to talk in a little bit of detail about each one of those. Radiation, we've talked about. It's a great way for heat to move through space. Microwave oven, perfect example of radiation. The sun, obviously, is another one. Conduction, on the other hand, think about a hot road when you're driving along. If you ever look at the temperature on the road compared to the temperature in the woods, for example, the road is conducting a lot of heat from its surface up into the atmosphere around it. It doesn't go far, maybe, the conduction process, but any air that's right in contact with it is being heated up. So the temperature, that's why sometimes you hear about, you can boil an egg on the blacktop or whatever, or cook an egg. And sometimes you can, but it's conduction that's doing that process. So another thing with conduction is that heat is not a good transporter. You know, the metal objects, the blacktop on the road, but we use fiberglass to insulate our house. Why do we do that? Because heat doesn't transport. Think about snow. I don't know if you ever noticed, but if you ever dig up the snow sometimes after the first snowfall of the winter and look at the ground underneath it, it's not frozen. Well, why is that? Because the heat can't get down. That cold air that's above it can't get down to the ground. It could be 20 degrees below zero on top of that snowpack, but that snowpack has air in it, and it's keeping the ground warmer. Convection, like I said, it's basically a movement of air upwards and downwards, cooling or warming. Obviously, when air rises, it cools, so it's transporting heat up and trying to warm the cloud, but at the same time, it's cooling as it's rising. If your air is inking, it's heating as it's sinking. It's being compressed. So that's convection. Now the phase changes of water. Well, all right. If you're in a gas and you go from a gas to a liquid, the molecules that were moving freely in a gas can't move as well, can they? So in order for that means that some heat must be released because their molecules are now going into a solid, a more compact state. So from going from water vapor to liquid requires heat being released. And if we go from a liquid to a solid, more heat is released. But if you go the other way, if you're going into a solid to a liquid, for example, heat must be applied to that solid. Those molecules start moving a little faster and they melt and they become a liquid. So in each one of these processes, and water is the only substance that is abundant enough in the atmosphere that we notice that changes state. So latent heat actually does a big process in the atmosphere to move heat around. And water, it takes a lot of energy to change it from a gas to a liquid or a liquid to a solid or back and forth. It is one of the elements that takes almost the most of any element. So that means there's a tremendous amount of this released. So when you see clouds form, that water vapor, there was a ton of heat released at that moment when those clouds are being formed. If you ever think about it, the clouds get colder. You see those little high cirrus clouds up in the sky. There's been a lot of heat released again because water vapor went from water vapor into a solid. So that had to release a bunch of heat into the atmosphere up there. So there must be other processes that are cooling it to remove that heat at the same time. So you can see all of these play a role in the transfer of heat within the atmosphere and the earth. Maritime climates, oceans do not like to change because they are water. They take a lot more heat energy to change. One of the things that's interesting is there's actually a net gain of energy on the Earth's surface, while the atmosphere actually has a net loss of energy due to infrared radiation into space. So there must be a transfer of energy from the Earth to the atmosphere in order to balance that change. And here's a big diagram basically showing you how complex all these transfers are. And if you're going to look at the actual temperature at your house, every single one of these transfers has to be thought of in order to understand what the temperature is at your house. That's why when you look at numerical models that actually forecast the atmosphere, and when they forecast temperature, all these processes are in there. Unfortunately, none of these can be solved exactly. They're all approximated, pretty good approximations, but they're all approximated so that we come up with an estimate of the temperature at your house, looking at every single one of these processes in the process. So, what I wanted to show you now is advection. We talk about cold air advection and warm air advection, moving heat transfer around. Advection is just that. It's advecting something from one location to another. So here is a cold front. We looked at those in the last chapter. The transition between air masses. Right here, the temperature is 55 degrees, 54 degrees. Look at the temperature over here in Ohio, in Illinois here, Wisconsin, 70, 66. Okay, summertime is not a great time to see advection. Winds, cold fronts are weaker, and there's not a lot of wind blowing usually. But there's northwest winds here. So if you take this 57, 54 degrees and you think about it moving to the east or southeast, at some point, if this front crosses through Wisconsin, there is going to be cold advection. This air is colder than the air back here. And that's what all we mean by cold advection. So if you had really strong temperature gradient, if the temperatures went from 60 to 20 in just a few miles here, that would be very strong cold advection. It wouldn't take a lot of wind. Or if you had 50, 60 mile an hour winds blowing here, you'd have fairly strong cold advection again. The two work together. The wind speed, how close that wind is to being perpendicular to the temperature gradient, and how strong the temperature gradient is, dictates how strong the advection is. And you can have cold advection or you can have warm advection. Oh yeah, you can advect moisture too, but we'll talk about that in another chapter. So this is some of what's going on today. And if you were to look at this today, you would say, oh, there's a high offshore here. We have south winds. So what's Ohio getting today? We're getting warm advection, bringing up the heat from the south. So it's just something to see and look at. One other thing I wanted to talk about. We talked about convection and heating a portion of the atmosphere. And it's really hard sometimes to see. You can really see it in the the wintertime. Sometimes summer is a little bit more difficult. This is just a sounding of the upper atmosphere. Temperature is getting colder to the left here. Right here, it's actually staying neutral. The temperature is not changing. What happens? This was taken at 8 o'clock last evening at Blacksburg, Virginia. Convection is heating this whole area. This is the area that convection is really rampant in, so that the solar radiation that's coming in down here and heating the ground is being lifted up through this area by convection. You can actually see this on soundings in the afternoon. Now, if I were to look at that sounding in the morning, when there isn't convection, remember the ground gets really cold. Let's go to the same area. Well, you can even look at this one in Oklahoma City. Look at how there's no layer that's nice convected layer like we had. What happens is the ground gets very cold. The heat, well, it's cold down there, so all the heat is getting transferred down towards the ground from the atmosphere. It's losing heat, so it's cooling. So you'll wind up with temperatures getting colder. So this is just showing you how the transfer process is actually working in the atmosphere. So if you have any questions, this week we're going to talk about global warming. I want to see your opinions about what's going on. I'm really looking forward to you trying to explain why you believe something. Because if we believe something, we should have some kind of an explanation for it. So look forward to that this week. And yes, please keep this one very civil. Everybody should be entitled to their opinion.